So it's like 8:21 in the morning and I'm gonna go over Bitwise operators. I literally just woke up, so I look like a mess. Bitwise operators are operators in the C programming language, and these operators are used to work on binary representations of integers. There are 5 particular ones in this video that we will cover, the basic ones, which is going to be the AND operator, the OR operator, the exclusive OR operator, the left shift and right shift operators. In any programming language, and especially in C, when you create a int variable and you assign that variable to, let's say, the number 12 here, this value is already stored in binary. Because of that, we can use our bitwise operators to specifically manipulate the binary representations of all these int values involved. So for example, the binary representation of 12 is this number. The binary representation of 13 is this number. And we have declared a variable z for our result variable when we use these operators and manipulate these two binary representations. And the binary representation for 0 is just going to be all zeros. And we have 8 bits here representing our ints over here, and in 8 bits is 1 byte. So this is what we're going to be working with. So when we think about using bitwise operators, I like to think of looking at these two binary representations and kind of working on them as a column. So let's first start using the AND operator in this case here. What the AND operator is going to do with these two binary representations is that it's going to go through each of the numbers here, and it will check that if there is both a 1 in each of these columns, this result binary representation will then also update to 1. So we can just go through it manually right here. So over here we have a 0 and we have a 1, so this bit stays as 0. This bit here is a 0 and this bit is also a 0, so this stays a 0. This bit is a 1 and this bit is also a 1, so this bit gets changed to 1. Finally, this bit here is 1 and this bit is also 1, so this gets changed to 1. So what we end up getting when we use our AND operator will be this binary representation here, which is going to be the exact same as what it is for 12. So what this line does is that it's going to assign the variable z to the int value of 12. Next, we're going to be dealing with the OR operator. So the OR operator is going to basically check if either of the two bits have a 1 assigned to it, and if they do, then it will update our result binary representation and add that bit with a 1. So in this column here, there is a 1 that exists between here, as there's a 0 and 1, so this bit will be 1. There is no 1 in the second column, so that will stay as 0. There is 1s in both of these columns, so that's going to be a 1, and there's a 1 in also both of these columns, so that's also going to be 1. What ends up happening after we invoke the OR operator here is that it's going to give us a binary representation of this, which is also, well, 13. So next is the exclusive OR, which basically in these two bits, they have to be a 0 or 1. It can't just be something where there is a 1 that exists between the two bits. There needs to be a 1 and 0. There has to be for it to update this bit to 1. So in this first case scenario, this bit does get updated to 1. This stays just the same because it's just 2 zeros. This does not change. 2 1s here, and since this is an exclusive OR, this would have to be 0 and this would have to be 1 in order for any changes to be made to this binary representation. And the same goes with the next 2 bits over here. So when we invoke our exclusive OR operator on these two numbers, 12 and 13, this will end up just being the int value of 1, since this is the binary representation of 1. Next, we're going to use the left shift operator, which is going to work a bit different from these 3 operators that we covered. But basically what left shift is going to do is that it's going to shift our binary representation to a certain amount that you want to designate to the left. So this is how it's going to work. So we were going to put our z value is going to be assigned to, let's say, x left shift by 1. So now z is going to be assigned to whatever the value x is, which is the int value of 12 in its binary representation, but it's going to be left shifted by 1. So let's take a look at this binary representation here. All left shift is going to do, and in this case, what we wrote here is that all the binary values are going to shift left by 1. So we can get rid of this and then just add just a bit right here, basically shifting everything to the left. And this would be our new binary representation. If you're catching on to a pattern that exists with the left shift operator, say I wanted to left shift the int value of 12 and its binary representation, I wanted to left shift it by 2. What I'd be effectively doing here is I'd be shifting this by 2. So this would be 1 shift, and this would be 1 shift again. And when you use the left shift operator, it effectively doubles your value. So when we left shifted 12 by 1 and the int value turned into 24, if we are to left shift the value of 12 2 times, it would turn to the value of 48. So it basically doubled from the value of 24. Finally, we're going to be dealing with the right shift operator, which is going to be basically exactly what the left shift operator does, just it shifts it to the right. So let's say instead of using our x variable, which is assigned to the int value of 12, and manipulate its binary representation, let's just use y in this example. Let's right shift this by 1. So we're going to take the binary representation here, we're just going to paste it here for manipulation, and we're going to shift all the bits by just 1. So we're going to shift these bits 1 spot to the right, and we have done it 1 time. So basically, what the right shift will do, in this case to the number 13, is that it's going to basically cut this value in half. Although, technically speaking, the right shift operator would have invoked a value that would have been like 6 point something something something. Those rest of the values after the decimal point is going to be just truncated and just not going to be there. So that is why 13 then and its binary representation will then turn into this, which is the binary representation of 6. So let's test the program out here, see that if it prints 12, 13, 1, 48, and 6 as it's supposed to. Yep, so it printed 12, 13, 1, 48, and 6, just as we wanted to. We can use bitwise operators to actually fix a program over here. We can substantially improve our function to convert a decimal number to binary number actually using bitwise operators, solely for the fact that an integer value is already stored as a binary representation. So all you need to use are your bitwise operators. So we have our same function name with the same parameter, which is going to be our desired number that we want to convert from decimal to binary. We're going to assume that the size of the integer is 32 bits. Again, like I said in my decimal to binary conversion video, I talked about how we just assume that we allocate 32 elements into our integer array so that when we get a binary representation of the integer that we want to convert, it will be able to express the full range of values that can be expressed in our program. So we don't need to create any integer array or anything. We just know that we're going to go through 32 bits of the integer that we want converted to binary, because again, the integer that we want to convert to binary is already in a binary representation within our code. All we have to do is basically just use our bitwise operators to check if the least significant bit, either 0 or 1, 32 times. So we're going to create a loop. So for int I is equal to 31, I will terminate when it is greater than or equal to 0, which will mean that when I reaches 0, there still will be one more iteration left, which will mean that we're checking all 32 bits. And we're going to decrement I so that it reaches to that, number of 0. So now we want to use our right shift operator for this. So we're going to make an int variable called j, and we're going to assign that to the integer value of n that we want to convert to binary, and we're going to right shift it by whatever is in the value of I in the current iteration. So now what we got to do is that we have to check if the least significant bit of our binary representation is either a 0 or 1. And if it's either 0 or 1, it will print out either 0 or 1. So what we're going to do if j, and then use our bitwise operator and then 1. What this line of code basically does is, so after the right shift has occurred between the number that we want to convert and the amount of times that it shifts right, depending on whatever the I value is at, that binary representation will be assigned to the variable j. And what this is going to do is, remember when we use our AND operator, it basically will put the two binary representations together, and it will check if there's a 0 and 0 or a 1 and 1. And using this AND bitwise operator is going to help us check if the least significant bit, which is going to be the first bit in our binary representation, it's going to check if it's either 0 or 1. So say we have the binary representation of 5, right? Let's say our j value was assigned to 5, and we have this binary representation here. What this is going to do with the AND bitwise operator, because we're checking through each of these bits here, and we're checking if this bit and the other digits bit, if they both match with either 0 or 1. And if they do, and if there are two matches of a 1 that occur, then it's going to come back as 1. And because we're checking it with only the int value of 1, this is going to be very useful to check specifically our least significant digit, which lies right here where I'm highlighting. Say we had the value of 4 instead, and its binary representation, this if statement would return back with the value of 0, since this does not match with this, since there's no 1 here and the least significant bit here, and there is a 1 here. So basically, what this loop is going to do is it's going to right shift the value that we want converted by however many times the value of I is assigned to, and then it's going to check if the least significant bit is matching together with each other, with j and the binary representation of 1. And if it doesn't, it's going to throw back a 0. And if it does, it's going to throw back a 1 in this case scenario. All the other bits don't really matter, since we are using the binary representation of 1 to check specifically our least significant bit. And just like that, just with these lines of code, we have created a function that can convert a decimal number into a binary representation. In the video where I did a decimal to binary conversion with the more complicated code, we use the number 375 to convert from a decimal value to a binary representation, and we're just going to use that number again so to prove that it works. So we're going to execute the code here, and we're going to pull out the number 375, and there you go. We have a 32-bit binary representation of the number 375. And as you can see here in these 9 bits, 10110111, that is exactly what we got on our binary conversions when we did it pen and paper, and when we had the more complicated function that did successive division over and over. But yeah, so that's how you use bitwise operators in the context of converting a decimal number to a binary number in a much more efficient way and less complicated way. Shouts out really to this user right here that gave a really good comment about making the program more efficient. So shouts out to this comment over here in the video where I created the complicated decimal to binary conversion function. Although the function I created was correct and it went through exactly how the successive division works in the context of getting a binary representation of a decimal, because of how our in values are stored within our program and computers itself, it's already binary representations. So all we have to use is our bitwise operators to get to those values. So thank you, Alan Salvolainen. I probably completely butchered that, but it was a really good comment that you made, and it inspired me to do a video on bitwise operators. Anyways, guys, thank you guys for watching this video. I have an exam literally like in a few hours about computer systems. So yeah, I'll catch you guys later. I might put more videos on computer systems and just see, because I'm enjoying it. And holy shit, excuse my language, my video for the decimal to binary conversion, the original one, got 900 plus views. That's crazy. That is crazy. It's because, like, little lore drop, but I've been making like YouTube videos. I mean, I had so many like breaks and hiatuses or whatever, but I've been making YouTube videos for a long time, for like 7 years, since I was in middle school. And I used to just make gaming videos, Call of Duty videos, and those never really got views. So to know that I'm doing something that I enjoy a lot more now, and it gets attention, and not only does it not get attention, but it's helping you guys. I mean, that's enough of that tangent. Thank you guys so much for the support and watching this video and all the comment interactions, and I'll catch you guys in the next video.